This video is going to be the second part of the two-part series that I'm making for last week's classwork. And I realized after watching the last one and going through it that there are a couple of things that I left out. So I'm going to go through this problem and be sure to include those this time. Okay, so if you guys remember the second problem from last week, it involved two objects. You had a police car and a speeder. And the speeder is speeding past the police car, and at time t is equal to 0, it just passes it, and then the police car sees that it's speeding and decides to accelerate and catch it. So let's kind of go through this one real quick. So the first thing that I had forgotten last time is that we really want to be drawing a picture here to go along with the story that we have here. So I just described the story, but let's actually put some more details here. So to start with, we have our car that is speeding. I'm sure you guys will maybe forgive me for my poor drawing. So this car is going with some constant velocity. It's moving, let's say, to the right with some velocity v0. And at the instant that it passes this motorcycle, and I don't really know how to draw a motorcycle, so I'll just try my best here. So it's a little bit more of a bicycle, but you gotta kind of get the idea. So there's our motorcycle, and this starts to accelerate with some acceleration that was given here as a sub m for motorcycle of t is equal to b times t. Okay. Now, as we're drawing this situation, there's something else that I left out that comes into play here, and that's drawing a coordinate system. So we always want to draw a picture and a coordinate system. And so the coordinate system that I'm going to draw here is going to be such that pointing to the right is going to be the plus x direction, and 0 is where these are both beginning at, where our story really begins. Okay, so now that we have our picture and coordinate system to go along with it, let's go ahead and break this into two pieces. So we have a piece for the motorcycle and a piece for the car. So I'm going to draw a little bit of a table here. I'm going to say that this is the car and this is the motorcycle. So in doing this, let's go ahead and derive our kinematic equations. That's going to be the first thing that we need to do. So the first part is just getting them for the car. And this is pretty straightforward because the car is going at some constant velocity, and so we know that if the velocity is constant, it's not changing. And changing velocity is what acceleration is ultimately related to. And so we know that the acceleration for the car, and I like to write these as generally as possible, the acceleration of the car as a function of time is going to be equal to 0. Now, the velocity as a function of time for the car is just going to be a constant. So this is going to be v0. And to obtain the position as a function of time for the car, we remember that in the last video we said that this was going to be equal to the integral of dv dt. Sorry, this is wrong. This is dx dt, which is equal to the integral of just dv ultimately. Or sorry, this is a v t dt. Okay. So what we can do is we can plug in our velocity. So this is going to be the integral of v0 dt. And so then we can evaluate. Now, this was something else that I had left out. There's only two types. There's only one type of integral and one type of derivative that I expect you to take. And these are things that you can just kind of memorize. You'll learn in your math classes exactly where these come from. So for the derivative, this is going to say that d by dt of t to the n is going to be equal to n t to the n minus 1. And then for our integral, we have the integral of t to the n dt. This is going to be equal to t to the n plus 1 divided by n plus 1 plus c. I'm not going to go into a lot of detail as to why these things are true, but these are just kind of equations that you can take to the bank. So that's an important box of information. I could, just for the sake of completeness, show you exactly where we're starting from. And again, this is this kind of table that I had in the last video. So we have a of t on the top, v of t in the middle, and we had x of t or y of t, depending on if we're talking about something that's going to be vertical or horizontal. And then if we want to go up, we take a derivative, because we know that v of t is equal to dx dt, and a of t is equal to dv dt. And if we want to go down, we do the antiderivative, or integral. Okay. And really, everything in these two boxes, the box that I have right here for this, for these definitions, or for how you do these derivatives. Oops, I'm losing some stuff here. Let's just not worry about that. We'll leave it where it was. You guys can find that fine. And everything in this box right here. That is everything you need to know for one-dimensional motion. Everything else comes from those things. Okay? And we'll see actually that when we do two-dimensional motion, there's not really that much to add to it. It's just that you're talking about what's happening in x and y at the same time, and that you have associated velocities in x, velocities in y, acceleration in x, acceleration in y. It's actually not too bad once we get these kind of fundamentals down. Okay, so let's continue on with this integral that we're doing right here. So we're just going to apply the rule that we have over here, and that says if I have some integral that I'm interested in when there's some t to the n dt, I'm just going to apply the rule, and this one's, it's kind of hiding the t to the n, because really what we have is the integral v0 t to the 0 dt, right? Because anything raised to the 0 power is just 1, so we could put that t to the 0 in there to take that into account, and then we can say, okay, well, if n is 0, then the rule says that we're just going to have, this is going to be v0, right? Because v0 is just a constant. Anything that I put in this integral here, if I put a constant here, that's just going to come out front. And I probably shouldn't call that a c. Let's call that an a or something, just to denote that there's some constant and it's different than the constant of integration. That doesn't affect the integral at all. Okay, so that's just going to come out. Then we have a t to the n plus 1. N here was 0, so it's going to be 1 divided by 0 plus 1, which is 1. So there's kind of a 1 in the denominator there that's suppressed, plus a constant of integration. Okay, so now we have almost our equation for the car, but in order to finish it, we need to determine what the constant of integration is. And in order to do that, what we're going to do is we're going to make use of the initial conditions. So what do we know about the car initially? Well, we're defining our coordinate system so that both the car and the motorcycle are at 0 initially. Okay, so that's to say that this is equal to 0. We can evaluate this function for 0. So this is v0 times 0 plus c. This is 0. So 0 is equal to c. And so that tells us that for the car, x sub c r is going to be equal to just v0 times t. Okay, let's put a box around that because we're going to want to remember that for later. We also have boxes around the acceleration and the velocity as a function of time. Okay. Now we get to the more complicated part, but it's not really that complicated because we're just applying the same rule that we have here, just for a different function. Okay. So for the motorcycle, what we have, and so this is part A, now we're getting into part B. For the motorcycle, we're told that the acceleration for the motorcycle as a function of time is going to be equal to some constant b times t, okay? So now what we want to do is we want to do really the same process, and we're going to say that b of t for the motorcycle is going to be equal to the integral of dv sub m dt dt, which is equal to the integral of a sub m t dt. Take this guy right here, we're going to plug him in right there, and so when we do that, we end up seeing that this is going to be equal to the integral b t dt. Now, this is where this situation is a little bit different, but it's not too bad. We just have a different power here. And so instead of being t to the 0, we have t to the 1. And so when we evaluate this integral, this says that this is going to be b t squared over 2 plus a constant of integration. Okay? That's the velocity of the motorcycle, function of time. Okay? Now, as always, we need to evaluate what this constant of integration is. And so we know that the motorcycle begins at rest. Okay? So it starts at rest, and so that says that the velocity of the motorcycle at time t is equal to 0 is going to be equal to 0. This is going to be equal to bt squared over 2 plus our constant of integration. We have to be careful here because our time is being evaluated, and so really this is just 0 squared. Okay? So this goes away, that goes to 0, and so that says that this constant integration here is itself 0, and so the velocity of the motorcycle, the function of time, is just going to be equal to b t squared over 2. Okay? We're almost there. Now, the last thing that we need to do is we need to figure out what the position as a function of time is for the motorcycle. In order to do that, what we say is that x of t for the motorcycle is going to be equal to the integral of dx sub m dt times, times dt. It's a little late when I'm filming this. I'm second guessing myself a little bit, but this is correct. And so this is going to be equal to the integral of b sub m of t dt. Take this part right here, and we plug it in right there. And so when we do that, this says that this is going to be equal to the integral of b t squared over 2 times dt. Again, we just apply the rule that we have over here for integrating different powers. And so when we do that, this is going to be bt cubed over 6, because we're going to get a factor of a third. 3 times 2 gives us 6, plus a new constant integration. Now, something to bear in mind, I keep calling all of these the same c. They're not really. I'm just being lazy because I'm going to get rid of them afterwards, but really they should all have different symbols. Okay, so this is our position of the motorcycle as a function of time. And so the last thing to do is to evaluate for this constant integration. So we can say that x sub m t is going to be equal to, we want to evaluate this at t is equal to 0, right? Because that's the initial condition we have. We see that in our story here. So we know that the initial position of the motorcycle is going to be equal to 0. And so this is going to be equal to b times 0 cubed over 6 plus c. This guy right here is 0. That says that this constant is 0. And so we have our final equation here. We have our x sub m t is going to be equal to b t cubed over 6. Okay? Perfect. So now we have all of our kinematic equations for the motorcycle and for the car. Where's our, it's right here. And then the last one was actually where we started. We started with this. Okay? So the next thing that we want to do is we want to determine what the units of B are for the motorcycle, right? So we have this constant B, but we don't know what the units of it are yet, or you might see what they are. But let's investigate this a couple of different ways. And so let's call this part C. So let's come on down here. So for part C, let's write down what our equations for the motorcycle are again. So this is A sub m of t is equal to B times t. V sub m of t is going to be equal to bt squared over 2, and x sub m of t is going to be equal to bt cubed over 6. Okay. Now let's look at the dimensional analysis. We know that the units of acceleration are meters per second squared, and the units of time are just in seconds. Okay? So we could algebraically rearrange this so we could see that B is going to be equal to A over T, right? A of T divided by T. And so if I want to find the units of this are just the ratio of the units of these guys, and so this is going to be meters per second squared divided by seconds, and so that tells us that the units of B are going to be equal to meters per second cubed. Okay? So that's what our units of B are, but we'd like to go a step further here and see, does this really hold for all of the equations that we have? And so let's check it, and let's kind of do it in reverse. So we know that B has units of meters per second cubed, and so let's look at our velocity equation. Let's see what the units of B times t squared are. So this is really the units of B times the units of t squared, which is really the units of B divided by the units of t quantity squared. And so we found what B was already. We can say that this is going to be meters per second cubed, and this is going to be times seconds squared, and so that's going to give us units of meters per second, okay? Which is exactly what the units of velocity are, okay? So this is the units of velocity. That checks out. Good. Let's do the last one. And so we have x sub m of t is equal to bt cubed over 6. We want to find the units of b times t cubed. Okay? And you guys can already see where this is going. This is going to be meters per second cubed times seconds cubed, and this is going to give us units of meters, exactly as we expect they should. Perfect. All right, so let's continue on then. We want to describe verbally in plain English, not just translating an equation, and mathematically write an equation for what it means for the motorcycle to catch the car. Make the appropriate plot. It does not need to be to scale. Explain how all of these are describing the same thing. And so verbally, if the motorcycle catches the car, then they're in the same place at the same time. Okay? So for D, car and the motorcycle are in the same place at the same time. Okay, so let's see what that means in terms of mathematics. And I want to come back here because I talk about a special time. So you guys remember in the last video I was talking about the difference between lowercase t as a variable and lowercase t as a value. When I'm talking about this being in the same place at the same time, I'm talking about there's a value of time, or like, you know, I could look at my watch and say those things were in the same place at 5 seconds or something. There's a particular value for it. And here I was a little bit cheeky and I said T, oh boy, somebody's going to get a ticket, or T star. But the point is, you can label these things whatever you want, but these are labeling them to tell you that these are values. This is no longer the variable, okay? So if I want to write this as an equation, this is going to say that x sub c for the car at t is equal to t star is equal to x sub m at t is equal to t star. So there's a very specific value of time. When I evaluate for that time, these two things are at the same point. Okay? Now let's see how we can do this graphically. So let's plot our positions. So this is going to be x of t, and this is t on the x-axis here, for each one of these situations. And so we could see exactly how this is going to look if we just come back to what these positions look like. Okay? So the first one, for the car, this is just linear. This is like a line. It starts at the origin and it goes up. For me, it's looking different than for you because of the flip, but you guys should be like, it goes up like that, right? And for the motorcycle, this is going to be a cubic, right? So this is going to go like t cubed. And so if you remember what those plots look like, we're only really interested in for times before, after the clock starts. This is going to look like this. So I'm going to plot. Here's my car. Here's my motorcycle. Okay, and so for our car, this is just linear, right? It's going to go up like that. Okay. For our motorcycle, it's going to start off lower, and then it's going to jump up like this. Okay. So that's what our plots look like, but we can detail this a little bit further. So here's just a dotted line going down to the x-axis. This is the time t is equal to t star. Remember I said that there's a particular value for time when this occurs? That's what this is. And if I look on our y-axis, or here our x of t axis, this is where x of t is equal to, for the car, is equal to t star, is going to be equal to x sub m of t is equal to t star. Right? So all of these things are saying really the same thing. And remember, I tend to say that a lot, that there's a lot of different ways to look at the physics, but they all have to say the same thing, and that's exactly what this plot is showing. It's the agreement between the equation and our verbal statement. Okay, so the next part, we need to obtain an expression for the distance the car has gone when the motorcycle catches it in terms of v0 and b, and show using dimensional analysis that the units of our answer check out. Okay, so what we want to do, we want to find the time, actually. We need to find the time first, and then we can plug it into that equation. So there's really a step that I left out here. But okay, so what we want to do is we want to say that for the car, we want to evaluate t is equal to t star, and we're going to say this is equal to the same thing for the motorcycle. But we know what these functions are. We just need to take them from up here. We take this function here, and we take this function here, and then we evaluate them at t star and set them equal to each other. That's going to give us what t star is. Okay, so this says that for this guy right here, his position as a function of time was just v0 t star. For the motorcycle, remember that this was the cubic that we had. This was going to be b divided by 6 times t star cubed. Okay? Now we just need to solve for what t star is. Okay? So the first thing that we can do in order to do that is we can cancel one factor of t star, and then we can move things around. So when we move things around, this says that t star squared is going to be equal to 6 v0 divided by b, and then we can just take square root of both sides. So that tells us that t star is going to be equal to T star is going to be equal to the square root of 6v0 divided by b. Okay, perfect. So this is giving us what T star is, but that's not really what we wanted. What we wanted was how far the car has gone by the time the motorcycle catches it. And in order to do that, all we need to do is evaluate our function. Oops. We evaluate our function. X sub c t is equal to T star is going to be equal to v0 times T star, which is going to be equal to v0 times the square root of 6v0 over b. Okay, perfect. Now, something I noted in here, and let's go ahead and check it. You'd get the same answer if you did this way, or if you'd plugged it into the equation for the motorcycle. But let's go ahead and check that. Go ahead and check that. So if I plug the same thing into the motorcycle equation, this is x sub m of t is equal to T star. This is going to be equal to b over 6 T star cubed, which is going to be equal to b over 6 times 6v0 over b to the 3/2. Okay. Now, what we can do here is we can notice that some things are going to pull out if we're careful about the way that we do this. So we can cancel some things essentially. So I'm going to write this, and you'll see why in a second. Really, b over 6 is b over 6 to the first. And another way that we could express b over 6 to the first is b over 6 to the 2 over 2. Okay. Now, let's play around with this to make sure that we're getting what we want here. And so this says that this is going to be b over 6 to the 2 over 2. And then this is going to be 6 over b to the 3 over 2 times v0 to the 3/2. Okay, I'm breaking this apart in a very particular way. You'll see why in a second. Now, really, b over 6 to the 2 over 2 is the same thing as is the same thing as 6 over b to the minus 2 over 2, right? Because I can just flip it over, right? Those are the same thing. Times 6 over b to the 3 over 2 times v0 to the 3/2. Now, the reason why I'm doing this is now I can subtract this exponent here from this exponent here, because they have the same base, right? So now that I can do that, this says that this is going to be equal to v0 to the 3/2 times 6 over b to the 1/2. And now to finally get this all to look like the other one, all we need to do is make the v0 of v0 times of v0 to the 1/2. Then we can collect everything together. And so really, this is the same thing as v0, there's a square root 6v0 over b. Okay? And that's x sub m, t is equal to T star. Okay? And that's the same thing that we found that x sub c of t is equal to T star is. Right? That's not an accident, right? Because we use that condition in order to find what T star is. And so if we plug T star into either the car equation or the motorcycle equation, we should get the same thing. Perfect. Okay, so that's that part. I don't remember which part it was. That was probably part E. So that was part E and part F. So we got the same, we did 2 parts at once, but let's call this E and F. Plus E and F. I'll put that right here. E, comma, F. Okay. Now the last part that we want to do is we want to consider that if V0 is 20 meters per second and B is 10, with whatever units we found it to be, Find the distance cars traveled and the time that it takes the motorcycle to catch the car. Using scaling arguments, explain why this does or does not make sense. If it does not make sense, how could you change what V0 and B are so that it does? Okay, so let's go ahead and plug these in here. So I've already forgotten what I said these were. I think it was V0 is equal to 20 meters per second, and B is equal to 10 times the whatever units this had. This was meters per second cubed, I believe. Let me just check this real fast before I move on. Yep, 20 and 10. Okay, so let's first calculate how long this is going to take. Okay, so T star, you remember, this is part G. T star is going to be equal to oops. See, I might be frozen here for a second. Yeah, we're fine. It's equal to root 6 V0 over B, right? So let's go ahead and plug our numbers in here. So this is going to be the square root of 6 times V0, which is 20. 20, when you're doing this, always try to plug your units in. This is a last check that you can do to make sure that units are working out. Divided by 10 seconds, meters, right? Like I said, it's a little late right now, so I'm not all here right now. 10 meters per second, okay. So now what we can do is we can cancel some things here, and so we can cancel this and this. We can cancel our meters. We can cancel factor of seconds. This seconds comes up here, so then this is going to be seconds squared. And so what we're left with is roughly the square root of 12. Okay? Now, root 12 it's between two other perfect squares, right? They're two perfect squares that this is around. So this is going to be 9 and 16, right? Because 9 is going to be equal to 3 squared, and 16 is going to be equal to 4 squared. So I'm going to guess. I'm going to guess at what this is, and we're going to say that this is roughly 3.5 seconds. It's somewhere in the middle. Okay. So that's what T star is. Okay. Now let's find how far the cop has to go before it catches the speeder. Okay. And so in order to do that, let's actually do it in terms of the position equation for the car. That one's a little bit simpler, right? We don't have to square anything or cube anything. And so that's just going to say that x sub c of t is equal to T star is going to be equal to V0 times T star. Remember that V0 I think was 20. So this is going to be equal to 20 meters per second times 3/2 is about 7 over 2. This is 7 over 2, or it's exactly 7 over 2. We can cancel this, and then this tells us that this is going to be 70 meters. Okay, so that's where the speeder is going to get caught. Now you can ask yourself how reasonable these numbers are, and I wanted to prove a point here, but the numbers aren't incredibly unreasonable, but they are kind of unreasonable. Because you think about how, if you're starting from rest and somebody's traveling at 20 meters per second, 20 meters per second is about 50 miles per hour. Okay? For those of us that live in the United States and use archaic units, this is about 50 miles per hour. Is it reasonable that you could catch somebody in 3.5 seconds, and you can do that in 70 meters? And it's not really. Like I said, I could have chosen more extreme values to prove this point more, but this is using our tool of scaling arguments to see, does our answer make sense, why or why not? And it just per the choice of values that I have here, they probably could have been more extreme for these guys, but these values don't really make sense. So what could we have done to make this a little bit more realistic? Well, the acceleration parameter beta, or B, should be smaller. So let's see what happens if we change this by an order of magnitude even. We can say, okay, well, what happens if I make b is equal to 1 meter per second cubed, and then we can run through our calculation again. So this is going to say that the time t star is going to be equal to the square root of 6 times 20 meters per second divided by 1 meter per second cubed. And so this is going to be equal to the square root of 120. This is actually really close to square root of 11. So 11 is 121, I believe. You guys can check my math on that. I hope I'm not making a mistake. But this is seconds squared, and so this is roughly 11 seconds. Okay, so there's t star. It takes 11 seconds now to catch the speeder. Okay, so let's see what that does to our distance equation. So this says that x sub c, t is equal to t star, is going to be equal to v0 times t star, which is going to be equal to 20 meters per second times 11 seconds. And then we can say, well, 11 is roughly 10, and so this is about 200 meters. Right? And that seems to make a lot more sense with our intuition, because 200 meters is about 2 football fields, roughly. Right? So that's a lot closer to what we would expect to happen than having some distance that's smaller than a single football field. Okay, so that's going to be it for this video. I'll see you guys in the next one. The next video I'm going to be doing is going to be over a lot of common mistakes that that people make and how to avoid them. So I look forward to making that one. I hope you guys enjoy it. All right, take it easy.